the past couple of sections, so 3C and 3D, were all about measures of center. So means and medians and modes and mid-ranges. But now in 3E, we're talking about the standard deviation, which is a measure of spread. And the reason for doing that is because if you look at these two data sets up here toward the top, they've got the same mean and the same median, both 75 in both cases. But they're not the same data set, right? Not at all. Because that first one's barely spread out and the second one's really spread out. So that's another thing that somehow we have to account for, how spread out the data set is, right? It looks like that certainly matters because these are clearly not the same thing. And we wouldn't want to confuse them for each other. So we got to have a way of quantifying spread or variation, and that's what the standard deviation does. So in this section, I put a whole bunch of backstory in here. We'll get to the computation stuff in a little bit, but I figured it looked really incomplete when I had it written originally with none of this stuff, so I stuck it back in. But the range, this is a terrible way to measure spread, but it's a good starting point because it's the easiest way that you could do it. The range is just the difference between the two extreme values, so it's the max minus the min. It's really sensitive to outliers. So like in this example, if you have the 105 as that last data point instead of the 10, look what happens to the range. Because if it's just the max minus the min, then for this first one with the 105, it's 105 minus 1, so it's 104. But then over here, it's 10 minus 1, so it's 9. So this doesn't look like it's really the greatest measure of spread because just 1 point being different can throw this way, way off. And you get a vastly different value for the range. There are situations where you actually use the range to approximate other things, and that's typically what it's used for. I'm not sure if we're going to do that or not. If we are, it won't be for at least a couple more sections. We'll have to see. But then if the range isn't going to work, or it isn't going to work very well, so we should probably be doing something else, what if we wanted to just average how far away the data points are from the mean? So we want to compute the average deviation from the mean, where the deviation is just, okay, for every value, how far away from the mean is that? So then if x is a value in the data set, then the deviation would be the difference between that value and the mean, so x minus x bar, right? Since x bar is the notation for the sample mean. And it seems like what you could do is just compute all the deviations. So for every observation, it's observation minus x bar. You just get all of them, add them all together, and divide by however many there are, and that should give you the average deviation. But that doesn't quite work because for every data set, the deviations always add up to 0. And that's the whole point of having this example in here because you can see them. If you add up the 3 negatives on the top, that's negative 14.6, and then the 2 positives on the bottom are positive 14.6. That happens for every data set. So that means if we just average the deviations directly like that, we're going to get 0 for every data set. So then we wouldn't be able to tell them apart. If we had one that was really spread out, we're going to get 0. If we have one where the points are all right on top of each other, we're going to get 0. We think, okay, that's not really working either because we want to be able to differentiate how spread out the data sets are. Okay, well then you think, well, maybe if you think about the deviation as just how far away it is and you don't worry about direction, like if it's above or below, then you could just take the absolute value. And that would be a reasonable fix, like it says down here in this last bullet point. But calculus was used to derive a lot of the advanced statistical methodology. So the thing that's used is squaring instead of absolute values. Absolute values make a mess in calculus. It's like if you know what the absolute value graph looks like, how it's shaped like a V, but it's like a hard V, the base of that V causes problems in calculus. So that's why it's squared instead of absolute values. Because if you're squaring everything, you're still ending up with all positives, right? Or I guess all non-negatives. You could have a 0 if your observation was equal to the mean, right? So we're going to have some squaring now, all right? And that's where the variance comes in. So the variance is what you get when you square the individual deviations, add them together, and divide by, in theory, it's the total number of deviations, but not necessarily in practice. So I'm just going to put in theory up there. because the way that you actually do it is to compute the sample variance, you divide by n minus 1 instead of n. So that's why I'm kind of putting that note in there. But then if that's how you're going to compute the variance, if it's based on all these squared deviations, it's the average squared deviation, or the average squared distance from the mean. However, if you're squaring everything, you're also squaring the units. And so that gives you things that might be hard to interpret. Like if you were looking at like a bunch of measurements of length. And so like, let's say you have everything measured in feet. Then what you're going to get for your variance is going to be in square feet. So like they're related, but they don't quite match up, right? And that's kind of the issue. And there, at least like the idea of square feet is like a concept that we have, right? Because then you have area, right? That would be a thing that you could have in square feet. But what if that's not what it is? Like, what if it's not usually a thing that you would square? Like, what if it's like, what if you're measuring liquids, right? And then you're like, okay, well, it's 50 milliliters and 68 milliliters, and you have all these measurements in milliliters, but then your variance is going to be in square milliliters. Right? Like, that's a hard thing to kind of wrap your head around, right? Like, at least square feet, like maybe that one you can kind of think about, like, okay, so that's area, but I can kind of see how this works. Square milliliters is just weird, right? It would be better if we didn't have that. It would be better if the units actually matched up. And then here's a weird one too that I wrote in here, that if the data set consists of weight measurements measured in pounds or kilograms, then the variance would be in square pounds, whatever that means, or square kilograms, whatever that means, right? Like that's hard to understand. It would be better if the units actually matched. And that's where the standard deviation comes into play, because the standard deviation is what you would get if you computed the variance and then took the square root. Because if you take the square root, you're also going to take the square root of the units, and then the units are going to match up. And the standard deviation is going to end up being a measure of the average distance from the mean, right? So that's good, right? That seems like ultimately that's probably a thing we're trying to shoot for. And the units of the standard deviation match up with the original units. I said that a minute ago, but that's a big important point, because that makes the standard deviation easy to understand, right? You don't have square pounds or square milliliters or anything like that. But then you can't have a negative standard deviation because it's an average distance, right? Distance can't be negative, right? So that's why you end up here, and you only use the positive square root. You could, in theory, get a 0 for the standard deviation, but in practice, that's kind of implausible. To get a 0 for the standard deviation, you need all values in the data set to be equal. So theoretically possible, in reality, you don't see that. Then the way that it works is the larger the value of S, the more variation there is. So if you have a little value for the standard deviation, that means your data set's all bunched up. But if you have a big value for the standard deviation, that's when your data points are all spread out. They're all over the place. And then the other things here, since outliers can have a large effect on the mean, and the standard deviation is based on the mean, right? It's the average squared distance from it. Then outliers would have a large effect on the standard deviation too. And then the last thing, and this is about what I mentioned up toward the top, like in theory you divide by the sample size. So you don't quite do that, and I think this is where we need the formulas and things. So the notation, it's a sigma for population standard deviation and an S for sample standard deviation. And then for variance, that doesn't have its own notation. Basically, since the standard deviation is the square root of the variance, if you look at that from the opposite perspective, the variance is the square of the standard deviation. So if the population standard deviation is written symbolically with a sigma, that's what that is, it's a lowercase Greek letter sigma, then the population variance would be sigma squared. Or if S is the sample standard deviation, then S squared is your sample variance, right? Since the variance is the standard deviation squared. We're mostly going to focus on the S squared and the S. We're going to be computing those when we get into the computations. So what we're actually going to need are going to be these right here. inside the red box. But notice the difference between the population variance and the sample variance, specifically in the denominator. So there it's a big N, here it's a little n minus 1. So that's weird, right? And I mean, I guess focus on the little n minus 1 mostly because that's the one that we're actually going to do. But the numerators are effectively the same. I know there's a mu in one and an x bar in the other, but that's because the population variance would be computed based on the population mean. That's what the mu is. And then the sample variance would be computed based on the sample mean. That's what the x bar is, right? And then the way that this works is if you needed a standard deviation, there isn't a direct way to get there. You would have to compute the variance first and then take the square root. So that's why there are these over here where it's just, if you're going to compute a sample variance, you compute s squared, you figure out what that is, then in order to get s, you just take the square root of it. And that's the kind of the way you have to do it. So what is this business with the n minus 1 and the n? Well, the capital N is supposed to be population size and the little n is sample size. But why do you divide by n minus 1? It's because if you divide by n, s squared underestimates sigma squared consistently, right? So you have this idea of where you want these analogous measures, like you want your sample variance to be a good estimate of your population variance. Just like you would want your sample mean to be a good estimate of your population mean, or a sample proportion to be a good estimate of a population proportion, if you want to go that way, right? If you have categorical data, I guess that's what you'd have to do there. But if it's always underestimating, then it's biased. So that's the thing where if we could fix it, we should. And the way that you fix it, effectively, it's multiplying by a corrective factor of n over n minus 1. But that would have the same effect as if you just divided by n minus 1 to begin with. So that's the simpler way to write it. Because otherwise it would be this divided by n times n over n minus 1. And then those n's just cancel, right? So you'd end up with the formula that's right there on the page. But that's the way that we're going to have to do it. It basically fixes that bias that would be there if we divided by little n instead of little n minus 1. Okay. So then, in general, like just if you're trying to draw conclusions in real life, less variation is better than more variation. So a smaller standard deviation would be ideal. So just for an example of why that would be true, let's say we're looking at the effects of a cold and flu medication where we want to see how often people should take it. So we're just looking at, well, how frequently do they show symptoms, or like how much longer after they take the medication do they start showing symptoms, that kind of thing. So here, most of the data is really bunched up. And I have this graph with a dot plot, which is like a histogram, except that each dot represents an individual observation. So you can count the individual observations really easily. But here, like almost everything's up here, right? And you've got those 3 points down there. But you look at this, you go, all right, looks like every 4 to 6 hours the symptoms come back for just about everybody. So it looks like what you'd recommend is take it every 4 to 6 hours, right? If your symptoms start coming back after 4 hours, you take it then. If it takes longer, if it takes 5.5, 6 hours, then take it every 5.5, 6 hours, right? Well, but these are in a nice little range, right? So it's a small standard deviation because even these three aren't going to affect it that much. They're going to get overwhelmed by how many data points are up here. And then instead, what if we had this, where here everything's really spread out, right? Basically from 0 up to 20, it looks like it's almost an even spread. And there you go, I don't know, right? Like if you were going to give a recommendation for how often you should take the medication, it's pretty hard to tell, right? Because some people, it looks like basically it doesn't do anything, right? It looks like the symptoms are there again right away. For some people, it looks like it lasts for as long as they'd probably be awake if they were getting a regular amount of sleep, right? So it's like, what would you suggest? Like, is it, do you take it every 12 hours? Do you take it every 2 hours? Just, to try to cover just about everybody? Like, it's really hard to tell. So in real life, like if you're trying to make a conclusion, it's easier if the standard deviation is small. But I suppose it just is whatever it is, right? I mean, it's not like you really get to dictate that. It's your data set that basically dictates that. So now, actually getting into the computations. This is what the homework looks like. And I figured that backstory was kind of worth it, just so that way it doesn't feel like this stuff comes out of thin air. But this is the part that looks like the homework. So we're going to compute the variance and the standard deviation of this data set right here. And if you're going to grind it out by hand, I think the best thing is probably to do it in a table like this, just to kind of keep things organized. So the mean, we're going to need that, right? You can see it in the table, but also the variance and standard deviation are based off of it. So the mean is x bar. You have to compute this first before you even think about the variance or the standard deviation. But then you're just going to add up all the data points and then divide by 7 in this case, since there are 7 of them up there. So I'm just going to add all these together. And then I'm going to divide by 7. And then numerator is 28, because 6, 3, and 1 is a 10. 4, 4, and 2 is another 10. So this is 28 over 7, which is 4. So then in my table, the mean is 4, and I'm just going to have 4s going all the way down. And what I'm going to do is I'm going to subtract left to right to get the deviations. So like here, this one is 6 minus 4, which is 2. And the next one is 3 minus 4, which is negative 1. And the same thing, 1 minus 4 is negative 3. We got a couple of zeros. We got a negative 2, and then we got a 4, right? And then we're going to square these deviations. So 2 squared is 4. Negative 1 squared is 1. And then just, if we keep going, you square negative 3, you get 9. You square 0, you get 0. You square negative 2, you get 4. And you square 4, and you get 16. And I guess I could have put the symbolism on top here too. So the observation, that's your x. The mean is your x bar. The deviation is the difference, so x minus x bar. And then the squared deviation, x minus x bar, quantity squared. Okay. Well then, in order to get the variance, we're going to need the sum of the squared deviations, which would be 4 plus 1 plus 9 plus 4 plus 16, which is 34, right? That's 20, 10, and 4. Then we need n minus 1, which is here going to be 7 minus 1, which is 6. So then the variance, which symbolically would be s squared. So that's going to be the sum of x minus x bar, quantity squared, over n minus 1. Oh, another thing, I didn't mention that earlier. That capital Greek letter sigma, the thing that sort of looks like an E, sigma starts with an S, and so does sum. And that's why it's used. So when you see that symbol, that capital Greek letter sigma, that means we're going to add things, right? And that's what you would do here, right? Because that numerator, it's, in words, the sum of the squared deviations. So it's that over n minus 1. So this is going to be 34 over 6. Or I suppose if you want to reduce that, you could say that's 17 over 3. Which for now, I'm not going to really do a whole lot there. I mean, I guess you could say, well, then this is going to be 5 2/3, which is about 5.667 if you round to 3 places. But then, like when I take the square root to get the standard deviation, I would just use the fraction. So in order to get the standard deviation, so that'll be s, but by definition, that's the square root of s squared. So for me, that's going to be the square root of 17/3. And that's how I'd put that into a calculator. I would just do 17/3 and then square root of the previous answer. And then what you get is about 2.380. And I think if you use the 5.667 and take the square root of that, it's almost the same. It's like 2.381. So, I mean, that's fine. That's okay. Like, that's just a difference due to due to slight rounding, so that's all right. But then we got our standard deviation there, and we got our variance there. Okay, so there's a decent amount of stuff that you have to do to fill out the table, but the individual steps aren't really that bad, right? You have to figure out the mean, but then you just do a bunch of subtraction. Then you do a bunch of squaring. Add those squares together, divide by n minus 1. That's your variance. Whatever that number is, take the square root. You probably want a calculator for that because you tend to have to take the square root of things that are kind of weird, like 17/3. That is doable by hand, but it's really long, so you probably want a calculator. All right, the next one, I wanted to have one that had negatives in it. So that's why this example is here. So over a 5-year span, the daily high temperatures on New Year's Day in Tin Cup, Colorado were 3 degrees, 25 degrees, -8, 17, and -2, which that, I didn't write it in, but for New Year's Day and there, that would have to be Fahrenheit, not Celsius, right? 25 would be way too hot for that area on New Year's Day. So definitely Fahrenheit there. All right, so the mean, again, we're just going to add up stuff. So x bar, add up stuff and divide by 5 since we've got 5 temperatures there. So we're going to have 3 plus 25 plus -8 plus 17 plus -2. And let's see, that's over 5. And if you add up the numbers in the numerator, let's see, 28, that's 20, 35. Oh, look, we're going to get an integer again. So 35 over 5, which is 7. And I should point that out. You don't have to get an integer for the mean. It just sort of worked out nicely for both of these examples. But in the ones that you have to do in the homework, which I think this only comes up a couple of times, they tend to work out to be integers as well. So I figured that part was sort of on purpose to get it to emulate the homework. But the mean is 7, so we can put those in there. And then the deviations, if we subtract, 3 minus 7 is -4. 25 minus 7 is 18. -8 minus 7 is -15. Right? Then 17 minus 7 is 10. -2 minus 7 is -9. And then the square deviations, if we start squaring those numbers, square -4, you get 16. Square 18, that's 324. You might need a calculator for that one. That's kind of an obscure one to know off the top of your head. -15 squared is 225. 10 squared is 100. And -9 squared is 81. Okay, so if you add those together, then the sum of the squared deviations is 746. And I guess I kind of wanted to put the symbols in here too. So x for the observation, x bar for the mean, x minus x bar for the deviation, and then x minus x bar quantity squared for the squared deviation. All right, so then the sum of the squared deviations is 746, and then n minus 1 is going to be 5 minus 1 here, which is 4. And then the variance, all right, so that's going to be the sum of the squared deviations. So sum of x minus x bar quantity squared over n minus 1. But that's going to be 746 over 4. And that works out to be 186.5. Okay. Well, if that's what the variance is, right, so that would be s squared symbolically. Then s, our standard deviation, that's going to be the square root of s squared, which would be the square root of 186.5, which works out to be roughly 13.657. All right, so we've got our two answers. So there's s squared, there's s, done. All right, the one thing I did want to point out, because this one's basically the same as the last one, except that there are negatives. So the things that I think you have to watch out for are right here. So that just to get that and that, because you're starting off with a negative and subtracting. So just be careful with that, right? Like -8 minus 7, that's how you get the -15, and -2 minus 7 is going to give you the -9. So in case you get negatives, that's the one thing where I think you have to be kind of alert, is when those show up, when you have to subtract the mean from some negative value. All right, then I did want to point this out. So this is a pretty good variance calculator, this thing here, which, let's see, I should have this open, but I don't. So I'll just go ahead and do it. Let's see, so it should be calculator soup. I thought it would come up. Okay, here we go. Yeah, that's it. So like for the one that we just did, if I put in our data set where we had 3, 25, -8, 17, and -2, and it is a sample variance that we want, and if I click on calculate, there are the numbers, right? Because we had 186.5 for the variance, and our standard deviation, I rounded to 3 places and said it was 13.657, but that's it, right? And then you go, yep, that was the mean that we had, right? And that was the sum of squares, right? Because that's the numerator, the sum of the square deviations. It was 746. So this will work for a bigger data set. I don't think you'll get one, but I figured just in case it was worth having something like this in here. You might have a calculator that can also compute a variance and a standard deviation, but not everyone does. So I figured an online calculator would be decent, and I looked at a few of them, and this one seemed to be the one that was the most intuitive. So if you want to do that, you can, if you have a bigger data set, or just to check your work, just to make sure you're doing all the computations right. That's kind of what I figured this was for. All right, so back to where we were. All right, figuring out just by eyeballing some data sets which one would have the largest and smallest standard deviation. There are a lot of questions like this in the homework. Most of this section, this is what the questions are. There are maybe 2 where you get the data set and figure out the variance, then figure out the standard deviation. But there are at least 4 or 5 of these. Like there are a whole bunch. So if the standard deviation is supposed to measure spread, and we said that a bigger standard deviation would happen when the data set would be more spread out. If you're looking for the biggest standard deviation, you're looking for the one where the data set's the most spread out. And you can kind of do this sort of eyeballing it to just like get a ballpark estimate. And what I would do is I'd kind of go through these one by one, and I'd go, let's see, this first one, like they're all in the teens, like they're all between 12 and 18. That doesn't look that spread out. This one, we've got numbers in the 20s. We've got a couple in the 30s, one in the 40s, one in the 50s. Like this one, right, like this is covering a decent amount of ground. This one barely covers any in C, right? Like C is definitely not the correct answer. C would be the smallest standard deviation, right? Because those numbers are all right on top of each other. It's all 35s and 36s, except there's one 37. So that one right there, I think we can safely say, even though we're not really asked for it, it's worth pointing this out, that this one has the smallest standard deviation. And then the last one, where they're all in the 40s, like this one and A look like they're about the same. And B would have the most spread, right? We got numbers in the 20s, 30s, 40s, 50s, right? There's a lot there. That's covering a lot of ground. So that one I would say would have the largest standard deviation. And that was really what we were asked for, right? So I guess that's the right answer. All right, well, there's one of them. And now let's do another one. I figured it was worth getting a couple of these in here. So which one has the smallest standard deviation? Again, you can just eyeball them, but if you want the one with the smallest standard deviation, you want the ones where the values are closest together. If you look at these, you go, okay, those are all between 93 and 96. That's pretty tight, right? Like those are pretty bunched up. That might be the right answer. B, they're all like in the 40s and 50s, but it's all like high 40s into high 50s because it looks like it's all between 47 and 59. C, got a couple in the teens, couple in the 20s, couple in the 30s. It looks like going from about 13 to 35. So it looks like if you just looked at the ranges, the range there is about 10. Here it's about 20. Here it looks like there's a lot of spread because you got numbers in the 40s, you've got numbers in the 20s and the 30s, and you got that 18. So what it looks like from here is that the smallest is that first one, right? So that's the smallest standard deviation, since those numbers are really, really bunched up, right? They're all within 3 of each other. In the biggest, it looks like, even though we're not asked for it, if we had to pick that one out, it's clearly the last one, right? That's got more spread than either of these two. So this one is the largest standard deviation. And actually, these go in order. And I wanted the last example to do this because, I mean, like I just generated these. Like I just used an algorithm to generate these, and I just specified what I wanted the standard deviation to be, and like for a population, then just forced it to sample. Samples the size 7. But I set this one up so the standard deviation increases as you go through them. So A is the smallest, then B is bigger than A, like that's got a bigger standard deviation. Then C's got a bigger standard deviation than B, and then D's got a bigger standard deviation than C. So that one, it's like if you go through the progression of A, B, C, and D, then you can see the standard deviation getting bigger. I kind of wanted that effect just once to show up like that. But that is how that one works. And I think that pretty much covers it. I know in this video and in these notes, I put in a lot of extra backstory, but it looked, I don't know, it looked incomplete without it to me. So if you don't feel like you need the backstory, that's okay. But if it helps to make more sense of it, then I guess that's kind of what I was shooting for. But that would cover everything about the standard deviation in 3E.